Hey folks, in this video, I'm going to go into a little bit more detail about what I referred to before as the philosophy of science. So bear with me for a minute. This is a topic that I like, and I'm going to introduce it by talking about how science producers are different than science consumers. Now, obviously, science producers are important. When you're trained as a scientist, you are trained to use methods that all have share a certain worldview that I'm going to talk about in the next few slides. Obviously, science producers are important. They create the science that improves our lives. But most people aren't science producers. Most people are science consumers. And this is perhaps the more important part of the class is not training you how to think like a scientist, but training you how to think like a scientist so you know how to critique and consume science. Often, I think this is the more important kind of role that most people are going to have in their life. I think of it like a numbers game, right? So a vast minority of people are going to actually be scientists. But, 7 billion people on the planet benefit from or get hurt from understanding or misunderstanding science. So, not everybody in this class is going to end up going to graduate school or being a scientist, out in industry or out at a university or whatever, but all of you are going to need to know stuff about science in your day-to-day lives. I want to give some examples now. Here's when being a consumer of science goes wrong. Here's when the disconnect between people's understanding of science and what the scientists actually produce becomes a problem. The first example is of vaccines and autism. So the vaccine autism link was found in 1998, but spoiler alert, we know today that it is not, there's nothing there. There is no link between vaccines and autism. The funny thing is, after a group of scientists found a link between vaccines and autism in 1998, immediately other scientists investigated this as well, because that's very alarming if it's true. And immediately other scientists doing studies found no link between vaccines and autism. So pretty quickly in the scientific community, this link between vaccines and autism was known to be not true. Why did that original team of doctors find that it was true? Well, this is a rare, fortunately, rare case in science of a scientific hoax. Decades later, investigative journalists found that one of the authors of that study in particular was engaging in many shady scientific practices and was probably aware at the time there was no link between vaccines and autism, but published that study anyway. Now, the scientific community knew very soon after this study was published that it was an outlier. They didn't know that it was a hoax, but they knew that it was mistaken in its findings. Why is it that even though the scientific community has known for close to 20 years that this isn't true, that it's still a widely held belief in the public? Well, here's the difference between being a science producer and a science consumer. As a consumer of scientific information, I don't blame you for not looking into the current medical journals that have people investigating this issue. That's a waste of your time, most of the time, to go investigate these things in depth. Once these ideas make their way out into the public, it's very difficult for members of the public to investigate issues like this that include all kinds of technical details. You have to have expertise in statistics and medicine and vaccinations in order to understand why the original study wasn't reliable. So being a good consumer of science is partly knowing just enough about the scientific method and how scientific consensus works to know which pieces of information in the public eye are reliable and which aren't. Another example of this is the issue of global warming. So anytime I bring this up, some students are already thinking, even though I'm from Tennessee, oh, this guy is some liberal college professor. That's why he believes in global warming. Well, I mean, if you don't believe me about global climate change, believe 99% of climate scientists. Okay, maybe you don't believe 99% of climate scientists. What about oil companies? So, by the way, each of the points on this slide, you have some supplementary materials on the class website that are optional, but you can go and investigate these claims that I'm making if you want. So it turns out, global climate change it was known among scientists for decades now, but wasn't really known and discussed in the public until the late 1980s. But almost immediately when it became known to the public, it became a political issue. Suddenly there's controversy. Why, when it's only known among the scientific community, there's no controversy, everybody pretty much has the same beliefs about climate change, but suddenly once the public knows about it, there's these different sides of people have different views of climate change that don't fit with the scientific consensus. Well, being a good consumer of science means understanding that just because an issue is controversial doesn't mean it's controversial in the scientific community the same way it's controversial to the public. Why exactly, how is it that people have known the truth of climate science for decades now, but the public still views it as a controversial issue? You can go through the supplementary materials to read the full story. So I don't want to pick on, the medical doctors and pick on climate science for doing a bad job of explaining to the public the science behind global warming in some instances, and defeating the misinformation. I also want to point to a theory in psychology. So these are examples of where misunderstanding the science on these issues leads to real problems for real people. So if you've not heard of the broken windows theory, it's based on a couple experiments by some very famous social psychologists. So in one of the original experiments, the researchers, they bought a used car and they cleaned it up, made it look pretty nice, and they left it in a bad neighborhood for a period of time. So in one condition, they cleaned up the car, it looked pretty nice, and they left it parked in a bad neighborhood. Nothing happened to it. What the scientists were trying to measure is whether somebody tries to break into the car, tries to mess with it, whatever. But all it took for the car to be trashed, according to this original experiment, was one broken window. If the team of researchers cleaned up the car, parked it somewhere in a bad neighborhood, and deliberately broke one of the windows of the car, okay, suddenly, according to the interpretation given, people go by, they see that the car has already been tampered with, and it's free reign, right? They take their liberties with the car. They smash the other windows, they steal things out of it, etc. So this is the origins of this broken windows theory, that if you want to reduce crime in a neighborhood, one very easy way to reduce crime in a neighborhood is to fix the broken windows. We extend this a little bit. You make sure there are no broken windows. You make sure there's no graffiti. You make these small changes, and this can lead to big changes in behavior. Somebody walks through your neighborhood and they don't see graffiti. They don't see small crimes or small problems. Then maybe muggings will go down. Maybe a violent crime will go down. Now, this is where, to give you the full story, you need to look through the supplementary materials that provided. It turns out this is extremely oversimplified. Even the psychologists who performed the original experiments where broken windows theory comes from will tell you that the public's interpretation of those findings is not warranted by their original studies. It turns out that the broken windows approach to policing and crime used by big cities is probably more harmful than it is good and doesn't achieve the goals that they originally set out to achieve. So here's an example of psychology being involved in this, where psychologists perform this experiment. They have this idea, and the original science was sound, and then they built off of that, but it gets out into the public, people misunderstand the science, and bad things result. Now, you as a consumer of science, and it's not only these kind of esoteric issues, but these everyday problems, you can benefit from being a smart consumer of science. So first is, we'll talk about evidence-based medicine. This is a movement in the medical community to only engage in medical practices in which we have proper evidence. Well, how do we determine what kind of medical practice fits under that category of evidence-based? Well, then we go back to the producers of science, and what did they consider evidence-based? It's not just in the medical field, it's also in the mental health field as well. There's been movements for a while now for evidence-based treatments in mental health. You know, this is an extension of what you do as a consumer. You have to make evidence-based choices. You can rely on word of mouth, you can rely on authority figures like doctors and physicians, but at the end of the day, there's got to be some kind of evidence behind our choices. Flipping to the other side of things now, for sure, let's talk about being a scientist. What kind of philosophy are you supposed to ascribe to if you are a producer of science? The most important one I want to start with is empiricism. So empiricism is an approach to gaining knowledge. We understand that there are many ways to get knowledge about the world. Intuition is something we use every day. Logic and argumentation is another important way of getting information. Hearing it from a friend, you know, sources of authority like peers and authority figures, right? These are all important for everyday knowledge gathering. But for a scientist, we have, special privileges to one type of information gathering, and that is empirical claims. Empirical claims are claims that can be supported with evidence, not with logic, not with intuition, not with argumentation. An empirical claim is one that can be tested with evidence. Empiricism is that philosophical stance, and the scientific method is the technique that uses that philosophy actively. So some examples of empirical questions be anything that you can get some kind of data to support one side or another. Video game playing is related to violent behavior. We can gather evidence for that. Certain policies that might be talked about in politics, will increase the health of a population or will decrease the health of a population. Non-empirical questions aren't, non-empirical questions can still be important, but we don't talk about them in science. Non-empirical questions can be some of the most important questions somebody talks about in their life. Somebody makes the claim, I'm a follower of Jesus Christ. That's not an empirical claim. I believe in Jesus Christ can't be something that you find evidence for or against, right? But if you say that, if you make that claim, that can still be extremely, often if you are making that claim, it's extremely important to your life. So non-empirical questions can still be important, but we don't, deal with them in science. In a similar vein, Let's talk about falsification. Okay, what does it mean for claims to be falsifiable? In science, we only want to deal with claims that are falsifiable. That means that the claim could be true or false. Okay, what does it mean for a claim to be possible to be true or false? Let me give an example of something that Karl Popper was often very critical of Sigmund Freud and many of his ideas. Sigmund Freud thought, for example, that young girls had penis envy. Young girls were jealous of the genitalia of young boys, and this is something that impacted their development. That and many of Freud's other claims, it's hard to find specific evidence that makes them true or false. And this is why most modern psychologists aren't able to really deal with many of Freud's theories, because they made claims that aren't falsifiable. There's no amount of evidence that can prove that claim true or false. But going back to an example I used earlier, violent video games are related to violent real-world behavior. That is a falsifiable claim, because if I can do some kind of experiment and find evidence that either shows that to be likely to be true or shows that to be likely to be false. So a falsifiable statement doesn't mean a false statement. It means something that I can do an experiment and find it to be true or false. Now, if you're thinking here, man, the previous slide, he's talking about empirical questions. It looks like empirical questions are often also falsifiable. That's why it's good to start with a base of empiricism as your source of knowledge. Because, for example, knowledge claims that are based on intuition are hard to falsify. If I intuitively understand something, then it's hard for somebody else to say my intuition was true or false, for example, right? So in science, we deal with empirical questions, and the best empirical questions are falsifiable. So we can test them using the scientific method. So, going back to the dichotomy in this whole presentation, the difference between science producers and consumers. Science producers, they try to use empirical methods. They focus on questions that are falsifiable. The scientific method is the application of the philosophical stance that scientists take. But science consumers, they don't have to be trained in the same philosophy of science that scientists are. But what can you do, right, if you don't want to get all that training? Well, you can still be critical of the different sources of information that you trust. When you're given scientific sounding information, can you make a quick judgment over whether it's just science sounding or whether it actually used the methods that scientists are trained in? Consumers of science, you have to use common sense, and you have to listen to peers and authority figures to give you knowledge about the world. Not everybody can go back and test and retest the basic physics that makes up modern engineering, right? You have to listen to engineers to tell you that, that building is safe to be in. But we should start learning to recognize which claims are based on a sound science and which ones aren't. But it makes no sense for you as a consumer of science to be constantly trying to falsify your own worldview, right? We have to learn what science to trust and what science not to trust, which one fits with our philosophical foundations that we need to be working in and which doesn't. So understand also a big important lesson is that just because you follow the modern day philosophy of science doesn't mean you're going to be correct. It's easy, even if you are a well-trained scientist, to make mistakes, to believe things that are false and you shouldn't be following. Our prior beliefs about any kind of our prior beliefs about any scientific endeavor are influenced by our cognitive biases, our wants and desires, and kind of just our baseline view of what the world looks like. We are constantly biased, and we're having to fight against that bias. It happens to scientists, and it also influences you as a consumer of science. Now, if you know anything about the culture wars over things like GMO use and climate change, you might not be surprised to find that if you identify as very conservative, so psychologists have tested this and found that if you're very conservative, you are less likely to agree with scientists, professionals, when it comes to climate change. So conservatives, they have blinders on when it comes to climate science often. But liberals, don't get smug yet, right? If you are extremely liberal, then you're also likely not to agree with current scientific consensus on things like vaccinations or GMOs, right? So people across every side of the political spectrum have blinders on when it comes to information that doesn't neatly fit their worldview. We found this in every group of people. Nobody is immune to this. We have to be constantly vigilant about what scientific information we're trusting and whether our biases are influencing it. How can you take down those blinders and trust good science rather than trusting science that you already agree with? Well, we're going to hopefully learn some of those techniques throughout this class. That's where we're going to end here. Thanks for your attention.